Well, thank you for the introduction. My name is Matthew, and today I'm going to talk about whether we can automatically detect bioshock and magnetopause boundaries with Cassini data. So just to recap what these boundaries are. So if you imagine you were Cassini approaching Saturn, then you will first encounter the bioshock, which is a boundary that separates low density cold solar wind plasma from the hotter, higher density shocked solar wind, which we call the magnetosheath. And if you keep traveling in, you encounter the next boundary, which is called the magnetopause. And this boundary separates solar wind plasma and magnetic field from the planetary plasma and magnetic field. And that's what we call the magnetosphere. So you may ask, why do we want to detect these boundaries? Well, there are lots of interesting physics that happen here, including the morphology, which affects plasma flows, dynamical processes, and which can lead to instabilities. And these in turn lead to more interesting dynamics. So these phenomena, by understanding them, can give us a better grasp of how mass and energy are transferred between the Sun and the Saturn system. And so that's a lot of reasons. And so how are these boundaries found currently? Well, mostly by eye, looking at spacecraft data and picking out intervals. And this process is not just time consuming, but also prone to human error, and it requires expertise. And this could slow down the science pipeline. With automation, the list of crossings becomes reproducible, and there is a potential for new discovery which might have been missed before. And the tool is reusable for existing and future missions without more time investment. So let's have a look at what some of these boundaries look like in data. Here is examples of bioshock crossings. We can see, let's just focus on the left plot. The magnetic field is typically very weak, that's the top panel, in the solar wind, less than 1 nanotesla. And we get a sharp increase in the magnitude as you cross the bioshock into the magnetosheath, because field lines pile up. And field fluctuations also increase due to turbulence. And for the plasma, you have low energy and low density and electrons in the solar wind, and the energy and density increase as you go into the magnetosheath. Here are examples of magnetopause crossings. So the second boundary that I talked about. The Z component of the magnetic field is usually negative when you are in the magnetosphere, whereas in the magnetosheath, the Z component of V, so here is the red color, it's close to zero, but it's highly variable. And it's not always the case as well. So this makes identification of magnetopause very difficult when you're just looking at magnetic field data. And here, plasma data can help. Typical electron gyro radius near the boundary is like 100 times smaller than the typical width of the magnetopause currently. And so electrons are unable to cross the boundary. And with that, you get two distinct populations, as you can see here, which is ideal for the detection. So now that we know what boundaries look like in data, how are we going to automate this, the detection? To simplify the problem, let's ask a yes or no question. Is there a crossing or not? We have some magnetic field data, we have some plasma data as input, we have some algorithm that will basically decide whether there's a crossing or not and output a yes or no. Why am I treating this as a binary problem? Well, there's a huge class imbalance in the data set. Most of the data do not contain crossings. And so by combining magnetopause and bioshock for this particular problem, we boost the number of positive examples we have. Here is a quick overview of the 5 stages of the data pipeline. So first, we have data collection. Luckily, Cassini has already done that for us. Second, we have preprocessing, followed by modeling the data with different methods. And then we have validation, and finally, deployment on new data. So now let's jump into step number 2, which is the preprocessing stage. Okay, so to reduce the scope of the search, we first pre-select the sections of Cassini's orbit where bioshocks and magnetopause are expected to occur based on empirical models of these boundaries. So that's what these two black lines are. And this gives us roughly 4.2 million minutes of data. And just for context, there's around 2,100 magnetopause crossings and 1,200 bioshot crossings in the current catalog, both of which are recorded as single timestamps. So we really want to reduce the data scope that we want to search. Second step of preprocessing, we want to reduce that even more. And so we employ an autoencoder for unsupervised outlier detection. And this technique helped us reduce the data by around 2 times, whilst keeping over 95% of the crossings in the catalog. So that's a step in the right direction. Okay, now on to the modeling part. We will focus just on 2 methods for now. The first one is a threshold method. So on the left, we have magnetic field data with 4 parameters for thresholding based on standard deviation, the BZ component, and their ratios between 2 windows. On the right, we have CAPS electron data, also with 4 parameters based on density and temperature moments for thresholding. The parameter values are computed using 2 sliding windows with a fixed gap. So I've drawn like a cartoon here. So these 2 red squares are the windows, and the gap in between is fixed. And why are we using this method? Because the algorithm is easily explainable. We can say exactly why a prediction was made based on the values of the 4 physical parameters which we designed to discriminate the boundaries. And to find the best set of parameters thresholds, we use Bayesian optimization to maximize the performance over all of the training years using the catalog of crossings. And the second method, we are using a convolutional neural network, or we call it CNN. So why did I choose to use this method? Because the current catalog of crossings were created by human eyes. So could we leverage machine vision as well to do the same? That was the motivation behind this. The diagram in the center shows how an input image of CAPS electron energy spectrogram is passed through the CNN, giving the output crossing or not crossing. How does it know what to look for? Well, just as I created the 4 parameters or features for the threshold method based on input data, the CNN automatically creates discriminative features from the input image in order to output the correct class label using the label training data, so the catalog of crossings. For the feature engineering, feature learning part of the CNN, I used this particular CNN called ResNet. I showed a schematic on the right. And the one thing that makes this particular design or architecture special is that it takes the previous input as the new input for the next layer. So it doesn't only take the current output. And this architecture has won image classification competitions in 2015, and it's lightweight enough for us to experiment with. Now, a problem you might ask is, do we have the same luxury as the threshold method to explain why we get certain outputs? In short, yes, and we shall see how later. Okay, so now we have the modeling of the data ready. Let's have a look at some of the results and see whether they make sense. Here are some predictions made by the CNN trained on magnetic field images. The first 2 are correct, but the last one is not. And we can kind of see already potential problems with using this type of technique for magnetic fluctuations like these, where they kind of look like magnetopause crossings, but from our knowledge, we know that these are just fluctuations within the magnetosphere. And here are some predictions made by the CNN trained on CAPS electron data. So here I randomly picked some of the samples, and all of the predictions were correct. And let's get back to our question, can we explain these outputs? So there is a tool called GradCam, which stands for Gradient Weighted class activation map. And this technique can help us explain the outputs using a heat map, which shows regions that are most discriminative for the neural network to output a particular class label. So in these examples, we show a red region which highlight the most important parts of the images, and they correspond to the discontinuities of, let's say, the magnetic field data or the discontinuity in the CAPS electron spectrogram. So you can see that the red region follows where the discontinuity is as I input different images. And this is what our human eyes will focus on too when we make our decision of whether something is a crossing or not. So let's compare some test predictions between the threshold method and the CNN method. The left-hand side is the threshold method, the right-hand side is the CNN method. Here we compare the predictions made using only magnetic field data. So the parameters on the left are based on magnetic field data, and the right-hand side, the images are of magnetic field images. And we can see that both threshold method and the CNN both detect the first two sharp crossings. So that's this one here and this one here. And the CNN, we follow the green line. The green line is the line for the crossing class. We also see a probability near 1 at the two locations. But for the CNN, it continues to predict crossing class for the majority of the remaining interval as well. And now if we look at the same event, but with CAPS data, we can see that the threshold method correctly predicts the first one, but not the subsequent crossings which happen. The CNN, however, identifies the first one correctly, and it has a period of no crossing as this 2-hour window slides onto the magnetosheath population. And then as soon as it captures the next crossing, we can see that the green line goes all the way back up to a prediction of 1. But an obvious limitation of the CNN method is that you don't get localized predictions just because we are using 2-hour windows. But you can already see that this could be quite useful to flag regions of interest. Here is an overview of the performance of both threshold method and the CNN method, based on test data from the year 2012. So data which has not been seen by both algorithms. The performance is measured using 3 metrics. We have precision, recall, and F1. Basically, we want all of them to be as high as possible. And we can see that CNN with the CAPS data wins on the recall and F1 score. So that's these two on the bottom. And whilst the ensemble threshold method, which uses both MAG and CAPS, wins on the precision, but you can see it's taken a huge hit on the recall. So further analysis of the misclassifications made by the CNN with CAPS images showed that the majority of them were actually intervals containing magnetopause crossings. And the next most common misclassification were of intervals containing bow shocks. And after correcting some of these labels, we find that actually all 3 precision, recall, and F1 reach over 90% for this particular test data set, which is great. And in the process of doing the error analysis, I came across one event which is similar to the Kelvin-Helmholtz vortex encounter, which Masters et al. 2010 discussed. And in this particular event, we see periodic sign changes in BY, so that's green line. And we also have striking ion and electron energization during this particular encounter. And so this could potentially be an interesting case study. But in summary, we can see that we can automate bow shock and magnetopause detection using just magnetic field and electron data, electron energy data. We compared 2 methods, a threshold method and a CNN method. And based on 2012 data, CNN approach outperforms the threshold method. But both methods are lightweight and effective tools for large-scale boundary surveys of spacecraft data. So can we just completely trust this? I would say not. We still should go through some of these selections by eye, just because some of the logic, like the sequence of crossings that would make a set of crossings physical, is not programmed into these algorithms or these routines. But these tools can definitely help, because given a shortlisted events, it will be a lot easier and less tiring to go through them manually. And you can go through many years much quicker. So further physical checks can help find some interesting case studies as well. And here are some potential further work, which I won't read, but that's pretty much for my presentation. I hope you learned something and it made sense. Thank you.